Today we're going to talk about how we can use machine learning to implement ARIMA models. And ARIMA stands for autoregressive integrated moving average. So real quick, let's talk about what an ARIMA model is. And in order to talk about an ARIMA model, we need to talk about time series forecasting. So if you guys remember from a few weeks ago, we talked about weather data off of a tandem drive in Yakima, Washington. And with this weather data and this lab that we were doing, I specifically mentioned that there was a chance that we were improperly predicting our model or improperly fitting our model because we were not accounting for date and time as factors in our analysis and our model fitting. And the issue with that is that weather is a time series. So weather is a sequence where we have a metric that is being recorded over regular time intervals. And because of that, that gives us a temporal aspect to our data, which must be accounted for because every prediction of future weather data is going to be reliant on previous or past weather data. In order to properly account for time as a feature within a data set, we have to do some pre-processing and pre-engineering to our data to properly account for the temporal aspects in our data. And one of the ways that we can do that is using an ARIMA model. So as I said, ARIMA stands for autoregressive integrated moving average. So this is a class of models that basically explains a time series based off of past values in the time series. So in a simple way, basically every value in that time series is dependent on a previous value in the time series. So these kind of models take into account the lag in the data and the errors in the forecasting from previous metrics in the data or measurements in the data. And so ARIMA models have three terms in them: P, D, and Q. So P is the AR term, the autoregressive term. Q is the MA term, the moving average term, and D is the differencing term. So P is basically our way of measuring the number of past values or measurements or metrics from the data set that are being included in the model. The Q is a measurement of the number of forecasted errors that are being included into the model. And D is the measure of the difference or the integration, the I in our ARIMA, the integration of that metric into the model. So the I is the way that we standardize our data. So that's the basics here. And to put ARIMA into words rather than mathematical symbols, the predicted YT, so the predicted value from your data set that you're looking for, is equal to a constant plus the linear combination of the lags of your Y, so the lags of your previous measurements, plus the linear combination of the lagged forecast errors, so plus the errors in your forecasting. So we can use this to determine and predict future values in a data set. And that's the basics of ARIMA. And ARIMA can be used for many different things, anything from business to statistics about weather to analysis of budgets or expenses or air traffic or sales or stock prices or inbound calls. So you can use ARIMA forecasting for almost anything. It's about focusing on one specific measurement and using that to predict other measurements. And this is specifically in the univariate case. So univariate is obviously one variable. On Wednesday, the next time we meet, we'll talk about the multivariate case and how we can use ARIMA models or more advanced regressive models to predict multivariate situations. So with that, let's go ahead and get started. So we're going to start by installing some packages. And today we are going to be switching over and working from Colab. Colab is a software package basically that integrates a Jupyter notebook, which is a markdown style notebook with Google's interface. So all you need to be able to use this notebook is a Google account. And the big benefit of using Colab is that anyone in here can go into the notebook settings and we can use hardware accelerators to train machine learning models. So most of the time, if you're working on machine learning on your personal laptop, you're going to use a ton of your CPU and also potentially a ton of your GPU. So you're really going to slow down your machine. Whereas if we're working in Colab in the cloud, we can use open access and free Google hardware. So we can use Google's GPUs and TPUs, tensor processing units, which a tensor is a multilinear, a way of describing multilinear relationships between variables. So it's basically matrix algebra on a very accelerated speeds. So we can use a tensor processing unit for free, which is awesome. So we'll probably be working here for the next couple of weeks. And again, this is a free resource. You have access to this immediately, and I'll share all this information with you. As always, we have our references. Today's project is coming from this blog right here, which is working on a package called SK Forecast from a scientist, Javier Ortiz. And it looks like this experiment or this project was done in September of 2022 was the last time it was updated. And we did not work directly from this project, but it is the base of the code that we're going to focus on today. So when you're working in Colab, we can still install packages, any packages we're interested in. All you have to do is add this question mark to the beginning of your line. So you're going to do exclamation point pip install and then the name of the package. And today we need to install NumPy, Pandas, sklearn, and SK Forecast. So we're going to go ahead and hit the run over here on the left hand side. That's going to run. I've already installed all those, so it should show me that we've already satisfied our requirements. And there we go. And we're good to go. We'll keep going. So we've got a bunch of packages to import today. We will not get to use all of these today. Some of them will be used in later videos because we're going to continue to build on this weather forecasting data set. And we'll use, when we get into the multivariable modeling and machine learning modeling for weather data, in our next session, we'll have to use some of these packages. So we can just hit the run cell over here. Ran in no time. And now we're going to start building our pipeline. So our pipeline today is actually rather long. If we go over to the table of contents, I've laid out the sections here. So we've got 1, 2, 3, 4, 5, 6, 7 different sections in our pipeline today in our first iteration. And then once we get to the seventh the seventh section, we will be on the tuning of our model. And after we tune the model, we'll retrain the model. And then we have 4 or 5 sections for the next 2 pieces of the work we're going to do today. So as far as building our pipeline goes, we're going to start with step 1, which is going to be data pre-processing in our checklist. For today, we are going to be working on the Atanum data set that I've previously sent to you guys. And I recommend that you download this data off of my GitHub. You can you can access the data directly from my GitHub as the CSV file. I would actually recommend you download or import the raw form of it, which I've linked right here. So it's just in text form. And we're going to save that as URL. Then we're going to come in here and create a new object in the pandas package that we're going to call data, and data will be equal to pandas.read_CSV, and that CSV that we're going to read is the URL that we imported above. Then we're going to say comma separator is equal to comma because it's a comma separated file or vector. And then after that, we're going to ask it to print out our data set for us. So let's go ahead and hit enter there, and we can check out our data here. So that took no time to run. We can see that the date appears to have been read in good. We are in perfect format. We have the year, then the month, then the day. We've got date 1, which is going to be used if we're doing any kind of sequential analysis. So if we wanted, instead of indexing by date, if we wanted to index by order, so time step 1, time step 2, time step 3 to infinity, we could do that. We have the minimum temperature, average temperature, max temperature, dew point, relative humidity, leaf wetness, average direction of wind speed, speed of wind, or average wind speed, max gust, 2-inch, temperature rating, which we don't have very many measurements of, and so on and so forth. So for today, as I said at the beginning, we are focusing on a univariate model today. So we do not need all this data, but this data will be useful to us as we continue to build on this data set. Another thing I want to point out is that in this corner here, you can convert these data frames to interactive tables. So you can take it from that kind of plain looking diagram into a more complex table where you can click and highlight and filter out and see what you actually want to see. But I digress. That is what we needed to see today. Next, what we're going to do is start to kind of condense down and start to prep and clean our data, as we always do when we start working on an experiment. So this is still part of step one here, our pre-processing. So we're going to come in here and call on our data object. And we're going to say data object is equal to the data object. Okay, so what we're doing here is subsetting the data object. So we're going to go from having all of these rows and only selecting the rows that we're interested in. And this again will be beneficial to us further down the line. Right now it's not necessarily helping us a ton, but we're going to ask for the date, the average temperature, dew point, relative humidity, speed of the wind, max gust, total precipitation, total solar radiation, and the evapotranspiration measured in inches. And then what we are going to do is take the data object and we are going to ask it to subset the date within the data object. And we're going to say that that is equal to the pandas package dot to data frame or date time. So this is basically going to convert from a string or integer, which is likely what the data is being read into a datetime format. And datetime is a package that is commonly used for pandas. So we're going to say we're going to convert to datetime of data date, which is our date that we are interested in. And we're going to give it the format of that date. And like I said, we are in year, month, date format right now. Once we've got that done, what we're going to ask Python to do for us is to actually set the date as our index. So in our original data set, you can see we have an index column right here, which is just representative of the row or the entry that we are on. So the row that we're reading at that time. But we actually want to use the date because we're working with the time series here. So we want to use the date as much as possible. So we are going to index by the date so that the data can be sorted and organized by that factor or that variable that is so important to our forecasting capabilities. So we are going to then set our index to the date. And then after we've set the index to the date, we are going to sort our index, which is the date, from lowest value to highest value. And then we're just going to take a look at it again. So notice in our previous data set, we were starting with data from 2012. When we run this section of our code, it spits out data from 2008. So we are certain now that the data has been ordered. Also notice we have reduced the number of columns down from I think 12 earlier to 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we've also gotten rid of our index, and the date is now our index for this data set. So that's kind of our cleanup process. So we've gotten through a couple steps of our data checklist. Now what we want to do is make sure that the data is in formats that we want to use and that we're not missing any values in our data set after we've cleaned and subset it in the way that we're interested in. So we're going to go ahead and use the data.isNull, which we've used in the past, to check for any missing values. Then we're going to print out how many values are missing. And then we're going to ask it for the information about our data set. So we're going to run that. You can see that we have no missing values at this time, according to our isNull function. And then when we look at the actual information about our data set, we can see that all of our values right now are in float 64s. So they're already being read as decimal integers, which is good. We can also see that all of the rows that we kept have 5,358 non-null values. So every row in this data set is currently filled. There are no missing values at this time. And we have an even or consistent consistent count of our variables across the board. So one variable or column, it does not have more than another variable or column. So we have an even data set overall. And then the next thing we have to do as part of our pre-processing and checklist here for our data is meet the assumptions of our model. So ARIMA models, autoregressive integrated moving average models, have a requirement where the data is required to be stationary. So when we say stationary data, what we're referring to is that the total average, or the line of best fit of the data, has a neutral slope. So yes, it can go up and down, but it is not constantly heading up, or it is not constantly heading down. So the slope of the line of the best fit of the data set, of the regression, is as close to zero as possible. So this on the right hand side here is an example of data that is not stationary, right? Because starting in our time series here, in 1974, we can see that our measurements of CO2 concentrations were around 330 parts per million. As we approach the end of the 1980s, you can see that we are up towards 350 parts per million. And while there's clearly seasonality to this data, we have ups and downs and peaks and valleys, the trend of the data, if we drew a line through every point, would be pointing up, which would tell us that this data is not stationary. There is a consistent slope of the line, and in order to handle non-stationary data, we have to perform transformations or calculate differencing metrics based on the correlations between points. Now, luckily for us, when we're dealing with weather data, weather in Washington specifically is naturally seasonal. We have 4 seasons a year. So we almost always have peaks and valleys that should revolve around a central point or a moving average in our data set. And so how we can test this is by simply graphing our data and determining if there is any clear slope to our data, or if our data looks relatively consistent if we were to plot a line of best fit. And in order to do this, we can simply subset our data set. So we're going to take the data from up above, which was our data object, and we are going to select one of the rows. Today, because we are doing a univariate analysis, we are simply going to model the average temperature in Fahrenheit and try to make predictions on that. So today we're specifically working with temperature data. As we move into the multivariate modeling, we will add in these other aspects like dew point and relative humidity. So we're going to subset the average temperature in Fahrenheit, and we're going to call that a new object called DF, or data frame. And then once we have the DF object, we can just simply plot the data based off of index and the value of the temperature, and see if the data is stationary or if we can see any slope or trend or seasonality in the data. So we'll go ahead and run this. And it's calculating. There we go. And we can see that, relatively speaking, in comparison to this stationary data set where we clearly have a trend up, or this data set right here that's not stationary and clearly is trending up, our data from the Atanum weather station appears to be relatively consistent. Yes, we have peaks and valleys, and we can see the seasonality of our temperatures over time at this location. If we were to draw or calculate a regression by hand, we likely would see a relatively flat line of best fit. So there is not much slope to this data. So based off of this plotting, I'm going to say that yes, we do meet the assumptions of stationality or stationary data that are required for fitting an ARIMA model. So we have met the assumptions of our mathematical model. Now, at this point, we are getting close to the end of our pre-processing of our data set. What we have to do at this point is decide how we want to split and train the data. So previously what we've done is used a built-in algorithm to the scikit-learn model selection package called train test split, which simply splits your data into the x-train, x-test, y-train, y-test, and then you just determine where you are pulling your X and your Y from. Now, with time series data, we cannot use the XY test train split algorithm there, and for multiple reasons. But the biggest reason is because with time series data and ARIMA modeling, we want to make predictions of future values based off of previous values. So the train test split algorithm is going to randomly select numbers from the entire data set and put them in the training data set or the test data set based off of the percentages that you've given it. Well, we don't want to do that. We basically want to tell our machine here that we want to take the first 60% of our data sets and call that our training data set. And then we want to take the next 40% of our data set and call that our testing data set. So we want to separate based on time here because time is such a significant factor in our model prediction capabilities or our forecasting capabilities. And it doesn't have to be 60-40. It can be whatever split you want. So in our case, I actually used 70-30. That's the percentages we worked with before. So 70% in this case of our total data from this Atanum data set is going to go in our training data set. 30% is going to go in our testing data set. And to determine how many days of our data set are going to go in each data set, we can look at our date time index here. So our date time index is telling us that we have 5,358 entries, and they range from 2008 in June to 2023 in February. So really recent data. So we have 5,358 total data points. And to calculate how we should split our data, we can simply just grab a calculator and go 5358 times 0.3. And there we go. So 30% of 5,358 is 1,607. So about 1,607 days should fall into the testing data set. And then the remainder of our data should fall into our training data set. So that's how we'll split it up. So to make that split, we're going to create a dummy variable or dummy object here that we're just going to call mask, MSK. And mask is going to be equal to the df, the data frame dot index. So the data frame again is our data of the average temperature per day. So the index of the average temperature and the less than the index minus 1, so the lag series, minus the time delta of days is equal to 1607. So basically what this says is we want to create a new object called mask, and mask is going to be less than the index, the total index of our data frame, and that data frame is taking the index minus 1 and it's subtracting 1607 days from the index. So we're just subtracting the total amount of time that we want to preserve for our testing data set. Once we've established our mask there, we can actually create our dummy variables, the df train and the df test. So the df train is going to be equal to df of the subset mask. And then we're going to do dot copy. So we're copying that data set, not creating just a view of it. So we want to create its own instance in our machine. And then we are also going to create another data set called df test, and df test will be equal to mask dot copy. So exact same thing basically, but it's going to be the opposite or the reverse. And then to make sure that we did that right, we can simply plot the data to look at the differences between the training data and the test data to make sure it was split properly. So we'll run that. It runs almost instantly, and the blue is showing us our training data. The orange is showing us our testing data. So what we just did appears to have worked exactly as planned. You can see, again, we're running from 0 to 80, which makes sense. That's our average temperature over time. And you can see that we have data shown in our training data set up until about 2019. And then last 1,607 days, which would be just about 3 or 4 years, shows up in orange from about 2019 through 2023. So it looks like it did exactly what we want. And remember, the reason that we want to split it up this way rather than having both the training and the test data being sparse or randomly selected throughout the entire data set is because when we're dealing with time series data, it is dependent on the previous value to be able to predict the future values. So we need to have it split up based on past and present and future. All right, so now we are done with step 1 of our pipeline. We've finished our pre-processing. We've got the data in the form we want. We've created our test and our training data sets. Now we can actually select our model. And in this instance, I already told you what model we're using because we're using an ARIMA model. So we're using an autoregressive model. And autoregressive is basically saying autoregression. So a regression is a model that predicts a continuous variable, and auto means self. So like an autotroph in biology is an organism that can self-feed. It can feed itself. It can produce its own energy. So an autoregressor is a model that can feed itself and predict its own variables or its own outputs based off of previous outputs. And in order to do this, we're going to use a random forest regressor. A random forest regressor is simply put basically like a binary tree in a way. So in a random forest regression model, you basically provide different combinations of a bunch of different trees, decision trees or binary trees that are trained on subsets of your data. And then you combine the different instances of the trees to make predictions and average your predictions and then create an overall random prediction of the data set. So it's a way of creating many instances of the same data set to basically work through a decision tree and try to get as close to accurate as possible, and then average the weights of those values to produce an overall decision for your data set. And so this is a rather simple model, but very powerful and with a ton of applications because time series is such a significant part of our world. There's many things that you can predict with time series. So that's step 2 of our model, right? We chose the model that we're interested in using here. Now what we're going to do is instantiate our model. Luckily for us, scikit-learn has a random forest regressor built in. It's called the forecaster autoregression, which is exactly what it says. It forecasts based on an autoregression model. And so we are going to create a new object. We're going to instantiate our model by creating a new object called forecaster, which is going to be equal to the forecaster autoregression function. And within the forecaster autoregression, we are going to name our regressor, which will be equal to the random forest regression, and has a state of 1, 2, 3, whatever number you want. And then we have to specify our lag value. Since we are dealing with daily weather information at this point in time, I chose a lag value of 7, which would be representative of a week-long index of time. So in theory, we are instantiating this model to be able to make predictions on 1-week intervals. We'll go ahead and run this and instantiate our model. It takes just a couple milliseconds there. We don't get any output, and that is expected because we did not provide the model any information. We basically just turned it on. Now what we're going to do is move into step 4 of our pipeline, which is fitting the model. So when we fit the model, we basically tell it what data set it's pulling from. In our case, we created an object called dftrain, which is the previous 4,000 days of data that we fed to the model, and we use that as our y variable, the thing that we want to predict, our response, and we're going to try to fit that into that data into the forecaster model that we just instantiated, and then we're just going to ask it to view the forecaster model. So we're going to hit that here. It's going to take a second to run to fit it, but not too long. We get a generic output. There's not a ton of information I need you to worry about right now. Again, one thing we can say is like it's showing us the window size of being 7. That's telling us it's the time period over which it is analyzing. So 7 days in our case. It's giving you the training range of your data from 0 all the way to 3,749, and the frequency of your training data, and then just some general parameters and outputs. Okay, so now we've got the model fit. The next step in our data pipeline here is going to be making predictions from our fit model. So the first thing we have to do here, because we're working with time series data again, is we've got to define the steps of time that the model is taking. So in our instance, rather than defining it as the total number of steps of time, which would be 5,358, what we want to do is provide it with the steps of the amount of time for the time series that it'll be tested on. So in our case, that is the df_test, that data frame That's the testing data that's 1,677 days long. And so we're just going to say steps, that new object that represents the total sequence of our time here, is going to be equal to the length of the data frame test, so that they're the exact same size. And then what we're going to do is ask it, or give it, the last window value. Last window is a reference to the window that is mentioned right here, the window size. So the window is basically the last point where the time series was analyzing. So it'd be the last location or the last index where the edge, the end of our window was. So our last window will be equal to the df underscore train dot ilocate, and we're going to say -7 through the end, so colon, which is representative of the end. And the -7 is because we gave a 7-day lag here. So we're immediately going to go from the end of our testing data set, or excuse me, from the beginning of our testing data set, -7, so that last window of time that the training data set was working on, we're going to provide a 7-day overlap between the training and the testing data set, and so that we can make sure that we're not missing any of those requirements for the overlap in our data, so we can make accurate predictions. So that's the last window. And then we can finally make our predictions here. So predictions, the object will be equal to the forecaster model that we calculated right here. And then with the forecaster model, we're going to ask for .predict. And then within predict, you have to provide some parameters. In our case, we only need to provide 2, which are the steps. So how many steps are there in the time series, and the location of the last window in comparison to the training data. And we created that as an object. So now we're just going to hit run on that and check out our results. This one does take a second to run, and that's because it's got, it's running through 3,000 variables here and trying to predict, and off of the fit model, how we should, or how the model should respond. So that's that. It took about 17 seconds there. Once we make predictions, we want to compare our predictions to our actual values, so to determine the accuracy of our model currently. So in order to do that, we need to combine those results, both the predicted values and the actual values from our data set, into a new data frame. So we're going to create a new object called results, which will be equal to pandas.dataframe. And within pandas data frame, we're going to request 2 new columns. One is going to be called actual, as in actual measurements, and that'll be equal to df underscore test, as in our testing data that we want to compare to. And then we're also going to give it another column called predicted, and predicted will be equal to the new predictions that we just made in our previous step of the pipeline. And then once we've got that new data set produced, we can actually plot these results and get a first look at our model before we compute some numbers of the accuracy of our model. So we'll go ahead and run that. Shouldn't take any time at all. There we go. So this is what our data currently looks like. So we've got our 70% of our data from 2008 up until about 2019. That represents our training data set. And then from 2019 on, previously, we had our testing data set, which you can see right here. So that testing data set right now is perfectly covered up, or it appears to be perfectly covered up, by the actual data set and the predicted data set, as we just calculated in our previous steps. Now, while this may look perfect, you have to remember that you are looking at 5,000 days worth of data. So there's a lot of overlap, there's a lot of squiggly lines, and a lot of fuzz, or a lot of many layers basically to dig through here, and so your eyes may be deceiving you. So rather than trusting these predictions ourselves, what we're going to do is mathematically determine the accuracy of our predictions using one of our potential accuracy metrics that we talked about in our last session. And today's accuracy metric that we'll be using is called the mean squared error. And the mean squared error is essentially a way of determining how far away a data point is from the line of regression for a model. So it is the measure of how close a regression line is to a set of data points. So it's basically a risk function that corresponds to the expected value of the squared error lost. And we can calculate it by taking the average of the mean of the error squared from the data that it relates to as it relates to the function. So obviously you don't have to do that by hand. In scikit-learn, there is a built-in function, a metric, an accuracy metric for mean squared error. So you can just type it in. So we're going to create a new accuracy measurement for error underscore MSE. So our measurement of our mean squared error for the total error of the model. So we're going to create this new object called error underscore MSE, which will be equal to the mean squared error of y true. So what were the true measurements for the data set, and that'll be obviously equal to our testing data. And then we're going to call the other one y pred or y predicted, which will be equal to our predictions data set that we created above. And then we're just going to ask it for a printout that says the testing error MSE of the error MSE. So let's run that. Our testing error MSE is 457.8457. Now, MSE is a measurement of the distance from the data point to the line of regression. So the bigger the number, the farther the more units or the further distance away that data point is from the line of regression or the line of best fit. So the bigger the number, the worse fit the model is. So honestly, right now, this model is not very well fit, and there's a lot of reasons why. The first one is that weather is not a univariate problem to try to solve. Weather is a multivariate issue by a long shot, right? We have all these other factors like solar radiation, relative humidity, dew points, wind, earthquakes affect it, the level of fogginess or cloudiness, the atmospheric pressure, all of these different parameters have an effect on the temperature and the average temperature over time. So we are not accounting for any of those variables at this point in time. We're only seeing if we can predict average temperature based off of previous average temperature. And so right now our model is telling us no, you really can't. It's not a super good fit. So what we're going to try to do is we're going to add another step into our pipeline here, which we'll call tuning. Which is basically just taking our hyperparameters and trying to determine which of our hyperparameters under what conditions may provide us with the best fit model for the thing that we're trying to predict. In our instance, to do this tuning, what we're going to use is called a grid search forecaster. So these grid search forecasters are basically a machine learning model for recursively searching through your data set and calculating matrix algebra operations, and then searching through random forest decision trees, those decision trees we were looking at a second ago, like this right here, and providing it with different metrics, which then are used to determine the optimal parameters for your model to get the best performance. And so there's a lot of steps to set this up, and we're going to walk through them right now. So the first thing you have to do is tell the computer how many time steps are in your data set. So in our data set, this is actually incorrect. We only have 5,358. I put 5,368, probably not a big deal. Then we also have to tell it our forecaster. So we're going to give it our forecaster model, which is the same model from what we used up above, and also the exact same random state and the same lag as of from above. And then we provide it with the lags grid parameter. The lags grid is essentially a way of telling how many different options to test, so how many different lag values the model should try to test. So in our instance, just based off of the example we were working from, they used 10 and 20. I tested 10 and 20 in this first round of optimization. And then we're going to give it the parameter grid. And the parameter grid has two primary attributes: the N estimators, the number of estimators, and the max depth. So the N estimators is the number of random trees that you want the model to search through in order to determine the best fit. So I gave ours a minimum value of 100 and a maximum value of 500 in this instance. And then the max depth represents the maximum number of decisions within each of the trees that are being searched in the parameter grid. So in our instance, we gave it max depths of 3, 5, and 10. So it's allowed to go 3, 5, or 10 levels into the grid, or excuse me, into each tree. And then with all those parameters set out, those are all the variables we have to initialize. Then we're going to create a new object called the results grid. And the results grid will be equal to the grid search forecaster, which is a built-in function in the scikit-learn package. And we are going to then provide it with a bunch of different parameters. So first off, we're going to tell it what its forecaster is, which will be the forecaster we instantiated up above. And then we're going to say what y is. So what is the thing that we are trying to determine or train? In our case, it's our response variable, which can be found in the df_train object. Then we're going to tell it what its parameter grid is, which we defined above, the lag grid, which we defined above, number of steps, which you defined above, refit, which is basically do we want it to refit the regression based off the parameters we provided. In our case, it is true. Metric, what is its metric for determining the accuracy of a hyperparameter? In our case, we're using mean squared error, so we just provide that as its option. Initial train size, that'll be equal to the df train variable, and we can even specify less or more of that data set. So in this instance, we provided it or told it to take half of the df train data set and use that as the initial training size. Does it have a fixed training size? False in this case. Return the best fit? Absolutely. We want to know what parameters are going to make this model work better. And then does the model need to be verbose? And that'll change based on the condition of the model or the model that you are fitting at this time. In this case, I left it false in this first instance. And these things, these hyperparameters and tuning these hyperparameters take a long time to run, because you got to remember you're doing thousands of matrix operations. So in this instance, I'm actually not going to run this model. I'm just going to show you the results. So basically over time, it calculates these matrix, it performs these matrix calculations one at a time iteratively. So it tells us at the beginning it had 12 different models to compare. And then it shows us a time printout and the progress over time. So the first one took 19 seconds, second one took 62 seconds, third one 42, and so on. So in total, this first model took about 17 minutes to run. So from our results of the first round of tuning, we can see that as we decrease the depth of the trees, as well as decrease the number of trees that can be checked, we have an increase in the mean squared error. So our predictability, our ability to predict our response variable, the average temperature, gets worse. As we increase the depth and increase the number of estimators, the number of trees, we do get a lower number, but not by much. So we get a mean squared error of 430 in comparison to 457 off of our original tree. So based off of that, I decided that maybe we can improve this a little bit and provide some more depth to the tree, and provide some more depth to our model, and also provide some more parameters or estimators to our model. So I went ahead and tried to fine tune the model again. I gave it the exact same initializing lag grid as well as the steps and the forecaster, but I upgraded the parameter grid. So instead of having just 2 estimator values, I gave it 10, 50, 100, 200, 500, and 1,000. And then for the depth, I gave it 3, 5, 10, 20, and 50, and then also none, so no options. And then as far as the actual results grid that we laid out, I laid it out in the exact same way, no differences besides the initial values or variables that we had to instantiate. And again, this one I'm not going to run. This one you can see over here took an hour to process. So training this model and fine tuning this model was an hour of time. Like I said, the previous one was about 17 minutes. So that's why we're using Colab, is because we can use these tensor processing units to quickly process this. If you were doing this on your laptop, this may have taken 3 hours or 3.5 hours even. And from our results, we had about, I think we had 72 total models to train or to test Yeah, 72 models to test, so it took an hour. And when we look at our results here, we of course have more data to drag through. And so what I did was turn this into an interactive model, and then we want the lowest possible mean squared error. So I searched and then sorted by mean squared error. And you can see that even with increasing the parameter grid, our search grid basically, by so much and so many extra variables and so many more possible trees, we really don't get that much more decrease in our mean squared error. Now the model is showing that it is a better fit, or we can estimate it and tune it to be a better fit by providing it a max depth of 20 and having our in estimators being 10 or 1,000. That's when we get our best metrics here. But it's still in the 400s. You know, we're not seeing the possibility of getting our mean squared error anywhere close to zero. So we're still way off of our line of best fit. But with that said, we can still take these parameters and update and retrain our model to make it a better fit. So that's where we're at now. So we've already run through our model once. Now we're going to rerun through our pipeline starting at step 3, where we instantiate our model and retrain it based off of the new parameters we just found above. So to do that, we have to create a new object called the regressor, and the regressor is equal to the random forest regressor, so that exact same decision tree that we were just talking about. And basically what you do with the random forest regressor is provide it the metrics of the parameters for the random forest that you are interested at that time. So in the first round, I ran this with the max depth being 20 and the number of estimators being 10. And I didn't see much improvement in the model as expected. But one trend I did notice in the previous results table was that as the number of estimators goes up and the depth goes up, we have lower mean squared errors. So one of our options in our results table here was an in estimators of 1,000 instead of 10, and that was only 5 units behind the parameters of 20 and 10. So I switched it out and changed our in estimators to 1,000 with still the same random state, and we'll see how that affects the model or if it improves our model at all. So that's our regressor. So that's a new object that we have. And then we're going to create another forecaster model. So we're going to call it forecaster 2, and forecaster 2 is equal to the forecaster autoregression function. And then we have to tell it what regressor it is using, and it is obviously using the regressor we defined above, so we can use our specific parameters and hyperparameters we're interested in. And then we have to provide it as lag variable. I kept the lag the same here, so I left it with 7 days or 7 time units. You do not have to do that. You technically could make this 12 or 20 or 24 or whatever you want. That was just me trying to keep it consistent with a week. So now we've instantiated our model. If we run this, we're not going to get any output, and that's a good thing. All we've done is basically it's turned the model on. So now what we need to do is go into step 4 of our pipeline again, which is fitting our ARIMA model. So we're going to call on forecaster2.fit, and then we're going to say that we want it to fit the df_train data set that we created way above. We're going to run that. This will take a little bit of time this time because we have 1,000 estimators or 1,000 decision trees that we are asking for this model to fit based off of our training data. So that is much larger than the 10 trees that we asked it to run previously. And the 10 trees runs almost instantaneously. Now, luckily for us, again, we're using Colab, so we've got tensor processing units which are specialized for these kind of situations, and so it only takes about 22 minutes to run. 22 seconds to run. Now that we have our model fit, we can actually start making predictions on our model. Again, we are going to have to tell it how many time steps it is going to be looking at. So rather than specifying a number, all we're going to do is ask for the length of our DF test. So our average temperature testing data set, how long is it? And that'll be equal to the steps here. And then we have to provide it our last window object again. The last window we are just going to keep as the -7 days. So our lag period was 7 days. So we're going to say that the last window object is equal to the DF train, so our training data set. And then we're going to ask it to locate the previous window based on our lag window, which was a 7-day window. So we're trying to create that overlap between our training data set in our testing data set right there. But then after it locates the last window, it'll run all the way to the end of the testing data set. And then with those two variables initiated, we're going to create a new object called predictions2, which is our predictions data set, which will be equal to the forecaster2 autoregressive model that we created above. And then we're going to say .predict, so please predict. And then we're going to tell it how many steps it has and what the window is. And then we're going to run this. And this one is going to take a long time again because it has 1,000 trees that it's running through. So this is a fairly large data set. Luckily that we have free hardware that we're working off of. So I will be back with you whenever it finishes. Okay, and our predictions are finally done running. This time it took about 2 minutes and 33 seconds, so just a little bit longer. But now that we have our predictions, we can go through the same steps from up above. So last time what we did at the end of step 5 was combined our test data and our predictions into a data frame and then plotted that data to see how well, to see if basically if our predictions aligned with our actual values before we provide an actual metric to test the accuracy of our predictions. So to do that, we create our object results again, and results is equal to a pandas data frame where we have a column that is our actual data from the testing data set, and then our predicted values from our predictions that we calculated above. And then we're just going to plot those on a regular time series graph. So our x-axis will be our time, our y-axis will be temperature in units. And when we run that plot, what we see is the exact same trend that we saw above. Again, the testing data set starts in about 2019. We can see that we have the same stationary data set, and it appears again that our testing or actual data aligns perfectly to our testing data. But again, we are working with a very large data set here with 365 data points per year. So there's a lot of information there packed in to this small graph, and we cannot see the level. We cannot determine the level of accuracy very well by eye. So what we need to do is move into step 6 of our pipeline and actually evaluate the model accuracy here. So again, we're going to use the error_MSE object, which is equal to our mean squared error function. And we're going to tell it what our true Y responses are, which will be equal to our df_test, so our testing data, and then what our Y predictions are, which are our prediction2 data set. And then we're just going to have it print out our error MSE. So we'll go ahead and run that. It takes almost no time. And you do see in this instance, we actually do get a much better fit in comparison to the previous model. So the last model, the very first model, had a MSE of 457, I believe, and this one we have 335. So still not great, but we decreased the distance between our line of best fit and our and our data points by about 120 units. So it is a better fit model, but it's still not perfect. We still have a lot of distance between our data points and our line of best fit. So to try to improve on this, one thing that we can do is create prediction intervals rather than just creating predictions. So instead of trying to say where exactly the point is, we're going to try to create a, for instance, a 95% confidence interval for where we believe the point is. And the reason that we may do this is because, again, for instance, today we're working with the average temperature metric. So we're already working with an average, which is representative of a minimum and a maximum value. And then it is, and we're calculating essentially the center point between those two values. So by creating a prediction interval, we may possibly able to capture more of our data and more accurately create predictions. And there's no difference between creating a prediction interval and what we've already been doing, except we are going to use a different prediction formula. So rather than using the predict function, we're going to use predict_interval to calculate a prediction interval for the 95% confidence interval for our data. So again, we're going to pick up here in step 3 of our data pipeline. So we're going to instantiate the model. So we're going to create and train a new forecaster. So this forecaster will be equal to the forecaster autoregression model. We're going to say regressor is equal to the linear regression here, and that our lags are going to be 15 days now instead of 7. We'll go ahead and run that. We're not going to get any output, which is good news again, because all we've done is turn the model on. The next thing we're going to do is fit the model. So we're going to call on the forecaster3 object, and we're going to say .fit, and then we're going to tell it what its Y value is. What is it predicting? What's the response? So in our case, it's just df_train, or our training data set. We'll go ahead and run that, and it looks like everything ran fine. The next thing we need to do is make our predictions. So we are going to come in here and create our prediction intervals. So our prediction intervals are going to be equal to a new object that we're going to call predictions3. It's the third thing we're predicting today. And that'll be equal to the forecaster3 model that we created and fit up above, .predict_interval, the prediction interval. And we're going to tell it that the steps in the model are equal to the time steps of the model, which we've defined up above as the length of the df_test data set. And then after we define the steps, we're going to define the interval. So from time 1 to time x, in this instance 99. And then in_boot is the number of bootstraps or the number of times that basically this data needs to be bootstrapped and computed over itself in order to ensure the accuracy of the data. So bootstrapping is basically a way of artificially repeating the experiment over and over again to increase the certainty of your data through mathematical means. So in our instance, we are going to bootstrap or repeat this process 500 times to try to ensure the accuracy of our predictions for this model. And then we're just going to ask it to print the first 5 for us. So we'll go ahead and run that. Okay, so our predictions finally finished running, and what we get basically is an output table of our predicted value, and then the lower bound and the upper bound, so the confidence interval for that value. So for example, at time 15, we have a predicted value of 55.88, and a lower bound of 46.59 and an upper bound of 66.43. So what we can do once we have these values is calculate our model accuracy. So we can again calculate our mean squared error of the y true being our df_test, and then our y predicted values being our predictions3 values that we just calculated based off of the location of the beginning up to whatever time you were interested in or whatever metric you're interested in. So it's the exact same output that we've been working with already. And then what we're going to do after that is combine all that into a data set as we've done previously also, and then plot it and see if we can visibly see the changes in our data this time in comparison to where we couldn't see the differences last time. So we'll run this big block of code here and see what we get out. So we can see that our prediction interval is providing us with a more accurate result than our regular predict function was. So our predict function was giving us an output of, I believe, 335. That was our error on the last model, 335. And this model gave us an output of 288. So again, not much of a change, but we were able to decrease our error by about 50 units. So a somewhat major change. We're slowly decreasing that distance as we iterate over this model and test out new techniques and new parameters. Now, when we actually look at our data, there's clearly something going on here, and we don't have to worry about this too much today because the plot is not going in a figure or anything. It's not being published. We are just working on this model. So we'll get to it in our next session. But what we can see is that the machine has gone ahead and decreased our range from 2008 to 2023, and it's changed it to 2019 to 2023. So it got rid of the majority of our data as it was plotting this data. And there's not really a clear reason to me why it would have done that. As I said, I'm not super stressed about it at this time. All we're doing right now is practicing working through our machine learning pipelines and iterating over these models and improving the fit of these models. So we did accomplish that. It's just that our plot is reading incorrectly. With that, that is the end of what I had for you guys today. So basically what the goal of today's lesson was to get into the nitty gritty of how do we work with these machine learning models. So today, technically, we were covering a supervised learning model with time series implications, or for time series forecasting. And we had to engineer the features of our data set and index based off of the time to make sure that we were accurately accounting for the time, the effects that time had on our weather data here. And kind of what our results are showing us is that a univariate model, which is what we're using today, so we're only looking at one variable and trying to predict based off of that one variable, just simply does not provide enough depth or information to train these machine learning models to accurately predict weather data, which is not surprising. Weather and climate in general, or environmental science or ecology, any of these kind of very complex systems are going to require intense multivariate analysis. And in actuality, for something like climate studies or climate science, they use supercomputers and computing clusters that run for days at a time to be able to predict these models and run these models. And so that's why we are having such high error here. That's why we have an error of 288. Yes, we were improving on this error, but we were not able to get anywhere near zero. We weren't able to fit the model to its best possible outcome. So this is what we will continue to work on. In our next session, what we're going to do is move into multivariate modeling of our weather data. So we're going to add in some more metrics and try to see if we can improve the fit of these models and accurately predict temperature based off of other things like relative humidity and dew point and solar radiation. So with that, that's all I had for you today. I hope you have a great day and an even better week, and I'll see you next time.